Now let us apply the concept of isentropic efficiency of nozzles to an actual nozzle. Say steam enters the nozzle at a pressure of 1000 kPa and a temperature of 320 degrees centigrade with a velocity of 30 meters per second. Then our steam exits with a pressure of 300 kPa and a temperature of 180 degrees centigrade. We want to determine the isentropic efficiency of the nozzle. For us to begin, we're going to express our conservation of mass and conservation of energy equations for a single stream steady state device, ignoring heat transfer, work, and changes of potential energies. And from our conservation of energy equation, our time rate of change of energy is equal to 0, our Q dot and W dot are equal to 0, and our GZ values are also equal to 0. Thus, our COE equation becomes 0 is equal to H1 less H2 plus the quantity V1 squared minus V2 squared per 2. If we express this in terms of our velocity at our exit state, V2 squared per 2 would be equal to H1 less H2 plus V1 squared. We have to evaluate this expression for our given states, i.e. the actual states. Using our superheated steam tables, EES, our irc.wisc.edu/property tables, we can find that our velocity at state 2 squared per 2 would be equal to our enthalpy at state 1, which is 3090 kilojoule per kg, minus our enthalpy at state 2, which is 2820 kilojoule per kg, plus our velocity at state 1 squared, which is 30 meters per second squared, per 2 divided by 1000 to ensure that our units are expressed in kilojoules per kg. And we get a value for our velocity at state 2 squared per 2 being 270.9 kilojoule per kg. Now considering the process if it were isentropic, our entropy at state 1 would be equal to that at state 2. Our entropy at state 1 is found to be 7.2 kilojoule per kg. Our enthalpy at state 2, based upon a function of temperature, pressure, and our entropy, i.e. S2 being S1, would be 2,810 kilojoule per kg. Thus, our velocity at state 2 can be calculated based upon our enthalpy, which is assumed from an isentropic process. V2 squared per 2 would be equal to H1, our initial enthalpy value, which remains unchanged, 3090 kilojoule per kg, less H2, which is H2S of our isentropic process, which is 2810 kilojoule per kg, plus the same quantity V1 squared per 2. Thus, at state 2, our quantity V2 squared per 2 would be 280.9 kilojoule per kg. Thus, our isentropic efficiency is found as our actual velocity at state 2 squared per our ideal velocity at state 2 squared. Our actual velocity at state 2 squared per 2 was found to be 270.9 kilojoule per kg. Our ideal velocity at state 2 squared per 2 was found to be 280.9 kilojoule per kg. Thus, our isentropic efficiency is 96.4%.